Let us start lecture number 2 of this module 3. Today I will discuss about the HVDC link control characteristic, both rectifier side as well as inverter side. In the previous lecture we saw this equivalent electrical circuit of HVDC link where we have your rectifier end and where we already derived the variable voltage, that is VDO R cos alpha, and this is a commutation resistance, and this is your inverter side, and this RL is your DC line resistance, and ID here, that is a control here, and that is derived by this equation. Also I ascertain that it is a preferred to go for the gamma control rather than beta control due to this negative resistance here, because sometimes operating the negative resistance your control characteristic may not be stable, and that is why we go for the here gamma. Another reason for this gamma control, that if you are calculating the beta, there is a possibility if there is a voltage dip of this side, what will happen, the commutation U angle will increase and there is a commutation failure. So one people suggest that why not we can go have enough beta, so that even though that can be taken care, but if you are taking more beta your power factor will be worsened, that will be poor. So it is always better to have a gamma control here, and this gamma is maintained certain degree, that is the minimum degree, normally it is 10 degree, and then we calculate the beta, we will see how beta is calculated, and then we operate in the constant extinction angle control. So here in this circuitry, if there are two possibilities, here if there is no voltage change in either side for a given set of power control, here your ID is fixed, voltage is fixed, this control link will operate without any change. Means whatever the power you want to control here, the ID is decided accordingly. If voltage here fixed, here this is alpha and beta are fixed, if there is no change here, the voltage in AC side, constant power will be flowing, and alpha is constant, here gamma is also constant. But we know our system voltages keep on changing, and due to this changes here, the voltage here, the firing angle alpha as well as here gamma should be controlled, so that we can operate this constant current in the DC link. Already we discussed why we are going for the constant current controller rather than power controller. Again I will explain later on why we are not going for the power control, why we are going for the current control. To see the impact of the voltage variation on both end, rectifier end or inverter end, here the voltage may increase, voltage may decrease, and normally the voltage increase is not very high because these are the very extra high voltage buses. Normally the voltage is not more than 5%, but the decrease may be anything due to the fault, etc. So we will see. Let's suppose, even though already we discussed about the voltage increase on the rectifier side on the previous term, now here I want to discuss if the voltage is increasing at the inverter end. Then what will happen? From that equation, that's the current equation, you will see if the voltage is increasing means your VDO I is increasing, and therefore your current in the link will decrease. Means I use this expression all the time, and here I can say this is your ID was defined as your VDO R cos alpha minus your VDO I cos gamma. Here your ICR, that is a commutation resistance of rectifier circuit, plus here your RL is the DC link resistance, and here minus it was your ICL. So you can see if this is increasing here it is minus, yeah, actually it is so small. So here if this voltage is increasing, means this is nothing but this your VDO, I am not writing IRI, here it is, we know it is under 3 EM by pi. So EM is basically the phase voltage, that's peak. If it is changing, now you can see the current, this is increasing, current is decreasing. Due to this increase here, what will happen, this side, this controller will try to, what it will do? It will also, this cosine here should also increase, because here we are not operating this one because this is slow control. So it will try to increase, means your alpha will be going minimum side, and it will be strict when alpha is reached at minimum degree, maybe 5 degree. Even though this controller here the current is not maintained to its rated value, then we have to exercise either this end tap changer or this end tap changer. So it is preferred to control the tap changer at this side because the voltage has increased that side. So it will wait, there is some time delay, and it will try to decrease the tapping so that we can maintain this one. Even though it is not fulfilled, then we have to go here to maintain the current here in this your link. So this, we have to operate our OLTC once we have exercised all this firing, that's the valve control. The valve control means either inverter side or rectifier side. This alpha and gamma we have to exercise first, then we have to go for these rectifier and inverter and OLTC transformer. The scenario becomes very worst when here there is a decrease in this voltage. Once there is a here sudden decrease, what will happen? This you can see this current is going to be very excessive, and due to this what we have to do, this we are not touching here, so this value should also decrease so that we can maintain here, and decreasing this means your alpha is going to increase, and alpha once increasing, because we have the limited reactive power support at that end, so this angle is also restricted to sometimes 10 to 20 degree. And still it is not possible, let's suppose the current is not maintained, because this voltage can go even the 0.1%, 20%, with the huge short circuit is there. So, and this may not even be sufficient, then we have to utilize our this OLTC transformer to make the current ever. So it is a tap changer is used. Now the another here, if your rectifier side voltage, this voltage is decreased, so what will happen here, we have to increase, and this increase again alpha minimum will be hitting limit. So overall I can say here what we are doing, if you are drawing here for given ID, here our ID is 1 per unit, let's suppose I want to operate, then we found that we are having this characteristic here, the constant alpha curve. If you remember we draw this, the chart, this characteristic is here, let's suppose. So this is basically your operating voltage where you are operating. This voltage is normally 1 per unit. Now you can say if here this current is 0, your voltage is higher. We can do it. We can just your tappings and transformer turn ratio in such a way that we can maintain here. Because we want our rated voltage should be 1 per unit and the current should be 1 per unit in the DC link, so that we can have 1 per unit power. Now whether we are decreasing or increasing beyond this one, it depending on the voltage rather than current. So this side we are having, this is your alpha control, and here we'll see this side we have no control of this, because we are trying to operate this gamma as a minimum. We can, even though this value can be, for example, this is what is your gamma. This gamma in this here, from your beta here, this is a 5, this is your U, and this is your gamma. You can go up to only minimum here, the gamma value, that is your commutation should be successful. So you can increase the gamma here, but if you are increasing gamma, it means your firing angle is also shifted here and the power factor is deteriorating. So this is maintained, the minimum. So it is possible that we can go for the gamma here more, but it should be also having certain limited gamma minimum, that is the gamma minimum should be there. So if you see, draw this characteristic, the characteristic for here, we should know what is the VD. If you remember our VD, when I was drawing here, this VD is individually we were drawing, this is the VD, this is the VD. If we were drawing separately, but it is not so. This is the characteristic where both your inverter and rectifier on the same axis. So we have to take whole link, where is your VD? Because we are having 3 resistances. If you remember for the rectifier, I just draw this VD, it is your VDO R, here cos alpha minus RCR ID. To visualize this, here see this equation. This equation we wrote for the rectifier. Similarly, we can write for our here the VDO I here cos gamma plus your RC ID. So here the voltages once we wrote, if you'll see our in the previous here in the previous curve circuit diagram, equivalent circuit diagram, here this VD, the first equation of the rectifier, we took this VD. For the inverter we wrote this VD. So if you are drawing the characteristic, the VD should be the same. Where you are talking here, the characteristic where you are taking the VD voltage here, VD. There is a two option. You can take VD here. This side is one equation, this side another equation, because VD is same, we are drawing VD on the same axis. So we can take from here this one, and either we can take VD here, these two resistances together. So if you are taking here VD, in the sum of the book you will find the VD people are taking here, somewhere people are taking here, absolutely no matter. Because we are taking the VD the same, either this point, because this side characteristic and this side characteristic together on the same axis. So here in this what I am going to write, if you are writing here, this is a minus resistance for the gamma. So this minus this will be there, the slope will be different than this. So normally this value and this value is approximately same. So only matter is this is either here added together, here subtracted together. So one slope will be more, one slope will be less. If it is 0, both having the same slope. Because the characteristic here you can see, if you draw here, this, if both are same, the characteristic will be the same one. So in this case what I am taking, the VD in our case, I am taking this as a characteristic VD. So this equation is 1, and another equation we are writing now, we are incorporating the RL as well to calculate the VD here. Means this voltage minus this voltage will be the VD in this case. So you can see here, this is, I have written in the first equation here, RCR plus RL is added here. Now it shows that you are having more droop compared to this droop. And then we are just drawing. Now you see this is your characteristic. This characteristic is, I can draw, this will be the more slope, here it will be less slope. This is your gamma. Because this is more slope, because here the slope, here we are adding RCR plus RL here, and this slope is a minus because we are taking the opposite of the inverter. So this is a minus term here appearing. So this slope is more because this is the slope of ID. So more slope is there, here is a less slope. So you can see this is more negative slope here. Here it is less negative here. Means the intersection of these two is basically your rated current which is flowing in the circuit. In this circuit, this the VD is there. Now this is the VD, and this is the intersection will be your ID. Now in this case, let's suppose this is the characteristic. So we can take this is your ID 1 per unit here. Hardly matter, thus you can have a slope. It's no problem. Now I want to establish that if the voltage this has fall down, or this side voltage has gone down, what will happen? Let us draw this is characteristic here. Let's suppose this voltage, inverter side voltage has dropped down. What will happen? This is operating as alpha minimum. This characteristic will have some parallel value here to this one characteristic. Now your ID will be this value. If you are not doing anything in the rectifier, inverter end voltage has gone down, and so what will happen? This will have another characteristic because this value is changed. This is already minimum we are operating. Other values are constant. Your ID will be here, which is increased tremendously. And once ID is increasing, so it is that we should not, because this may damage your line, and also it may damage your valves, converter valve, because more current will be flowing, more loss, and it may puncture your rectifier converters, thyristors. So it is believed that we should operate your rectifier end to control the current, that it should not increase by changing alpha or changing the VDOR. So this characteristic, what we do here, we want that this rectifier end should control the current. Now what will happen? Now even though this voltage has gone down, your new operating point is this. We are not going now here only, because this is your alpha minimum, because we cannot go up because alpha minimum is there and your all OLTC is exercised. This is the boundary of this characteristic. Now we are having another characteristic here that is called constant current, and this should be controlled by rectifier here, even though your voltage of inverter end is falling. So what we require rectifier should control the current of the link, and that is called your constant current controller. So your rectifier control characteristic here, you see your this here. Now there is even the possibility, now this characteristic here, let's suppose even though it has gone down here, we can take any characteristic of this gamma. So normally we can operate at this knee point, but it is preferable that we can operate slightly lower than this, and here the gamma characteristic is there. Let's suppose this is the gamma that is called CEA, constant extinction angle control, because this is a characteristic related to your gamma minimum, and here the intersection point is your operating point. Now another characteristic you can see, now even though this voltage has fallen down, this voltage is going down, what will happen? There is a possibility you are here. If this voltage is down, means your this value is reduced tremendously due to the fault, etc. Even though you are hitting the alpha minimum characteristic will shift here, because it will come down. This is the slope is the same, because the minimum value, only this constant is reduced, means we are going here, the voltage is reduced. Now you can see you are having one characteristic here and another characteristic here. Both are not intersecting to each other, and what will happen? Your converter will run down and there will be no power in the DC link. So in that extreme condition, what is advisable, that our this inverter should also have a current controller, because we want to current should be controlled. We should have another control characteristic here, and this inverter should take. But we cannot keep both current rating for the inverter and the rectifier together, because there is a possibility there is n number of point of operation will be there, and there will be hinting in the control. So always we devise another sum, it is called the current margin. We get some 10% of the rated value here. Normally it is your 0.9 of this per unit. So your complete characteristic here, now you can see we are going to have the control characteristic of this. In this mode only I am talking, means the first coordinate, this is your alpha minimum, and then we are having the CC, constant current control. Then we are having here this slope is less than this, and then we are having another one here. This is your CEA, constant extinction angle control. This is your constant current control. This is also constant current control. Here this value is called the margin, ID margin, and it is normally 10 to 15% of rated this current, link current. This is also called constant ignition angle control, CIA control. So this is a general characteristic that is required, but we will see even though for several cases this is also not sufficient, and we'll see there will be some modification in this control characteristic. Here we are talking only, this is your, if this is a rectifier, this is basically for inverter. Here this is your rectifier characteristic. Now here few points I have again written. Why we never use the beta control? Because you can say that we can use this equation rather than this equation. It was possible to maintain the current. Here as a higher value of B can be used to avoid the commutation failure, but the power factor will be poor, so we never go for this. What we do, we calculate the gamma. Based on the given value of gamma here, we calculate the beta for a given current. So that's why, and in that case we are maintaining gamma, that is very, very useful. But there is also possibility once you are computing this beta and then your voltage dip is there. Because you had computed the values based on the previous instant, now once you are going to fire it, voltage has dropped down and then commutation angle again increases. So it is also not 100% assured by the gamma control. There are some risk, but still that risk is less than this risk. So we'll see, as it is written here, the value of B is calculated for fixed value of gamma using the following equation. This is the equation, rather this ID equation which we derived already. You can see the beta is calculated, this is known. If this you are known, you are measuring the voltage here, other values are known here to you, you can calculate the beta very easily from here. Now, see there are the risk, and those risk here basically as I written here, is still there is substantial amount of risk in the commutation failure. Due to these points, you can see the computation is based on the reduction of the three-phase symmetrical fault. Even the voltage has gone down while calculating before that even. What you are doing, this EM which you are using, this is, you are assuming this three-phase voltage balance value. But there is a possibility, if there is a line-to-line fault, you are taking one phase voltage, that may be the same, but you are taking another phase voltage that may be changed, and that may cause your commutation failure. So it shows that there are so many faults like L to G fault, there is L to L fault, so asymmetrical faults are there. If there is a symmetrical fault, means three-phase fault is there, this EM will be reduced and then you can calculate accordingly. But for the asymmetrical faults, here the overlap will increase for that phase and then it may create problem for other valves. Because whatever you are calculating here, that is calculated the instant for all the valves. But you know, we had the three phases here, and from one phase only the two valves are connected. If there is some problem here, that may cause problem to other valves. So there is one risk here. Another here, the rate change of the DC current may be significant with the reduction of the AC voltage. What happened? We are taking the ID as a constant. ID may not be constant because suddenly it is changing very fast. If it is a slow, it is okay, because by that time we are firing again and you will take care. But the sudden change in the ID may cause your commutation failure because your calculation may be not accurate. You may increase at that time. Another here, the commutation failure may occur when the voltage reduction takes place just after firing the valve. As I said, here you have here calculated this beta, and this you are given the firing pulse here, and after that, just let's suppose there is a fault in the inverter side, your voltage will reduce and this EU will increase here, and you are not maintaining gamma minimum, and there is a risk of commutation failure due to this voltage dip. But again, this probability of this is very, very less, very rare compared to others, but still we use this one. To avoid all these things, it is not only we should measure this EM, we should not only measure this ID, we should also measure other phase voltages. For example, here I have written that we can go for, we have to calculate, measure the amplitude of commutation voltage. This is your EM, the commutation voltage magnitude. Then we have to calculate the phase of the commutation voltage, because which valve is going to come. So that phase voltage also. For example, here one phase you are taking, you have to take other phases voltage as well to take care of calculation of this. You should also take the direct current magnitude, which is going to change. It is not fixed value, you have to measure it. And also sometimes you have to see the rate change, how it is very fast, then that correction is needed. Certain. So we'll see this correction is change in ID is also taken care in the deciding the what will be the angle, that is alpha or gamma controller. Now we'll see there is some change or some in this circuit. You can see just I draw up to here. Even though this characteristic, as I said, we will see there is just some modification required, but this is the first coordinate when the power is flowing from your rectifier to inverter end, means your power flow from here. As I said, this is your rectifier, the power is flowing here, that is ID, and this is your VD positive. VD we are taking including your line as well. Here it is your VD. Now, if the power reversal is there, now you come this side. What happens? Now you can see this is operating here, this CEA, the constant current, now it is going to be alpha minimum. Because now this inverter which was here now operating as a rectifier. And in the rectifier it is a alpha minimum control is there. So this is three part. One is your alpha minimum control, this is a constant current, and then here the CEA, that is a extension angle control. Means the rectifier which was here alpha minimum and it was the CC, now it is going in the inversion or the power reversal case, it is your gamma and it is CC. So you can see this is half of the current. For this case it is a CC and then it is your CEA control. Similarly, when it was inverter, it is a CEA then CC, but here alpha minimum is going to be controlled. Now you can see here the intersection point is P is possible in the rectification, but here there is no intersection in this one. So you cannot operate with this characteristic in the power reversal case. So what we do, we never change the characteristic, only we change the margin. You can see here the rectifier in the normal case, the rectifier was rated at the ID, which is rated current. Now there was some margin here, IDM, IM here it is written. Now what we do, we change it here in this mode. Because this is only 10%, so 10% change setting is very easily possible. If you are going to change huge amount, it is not possible, but 10% you can change the reference. So now you can see here, this is going to be increased, this current. Earlier this current was less than your rectifier end current. Now this is coming this side and this is going this side, and then we are operating an intersection point is possible. So in the power reversal what we do, we simply this CC is coming this side and this is going to be this. Means this is high, in this case larger value, this is lesser value in the inverter end, and now in this here this value becomes less and this value becomes larger. So that we can have the intersection, and this will be your operating point. This will be your VD, this will be your ID, and this is the power, because negative here the power is flowing from this side to this side. But again the current is flowing in the same direction. You can see current is always positive, only we are changing the voltage. So when this was a rectifier, your VD was positive here and the current was flowing here, we had this characteristic on the top. And the power is flowing from this end, this is a power, and going to this end. When the power reversal is required from this end to this end, for the power which is flowing here, we have to change. Now this is operating as a rectifier, and only we have to change the ID setting of the controllers. Now this controller, earlier it was inverter, now this should be the current of this margin, and we have to reduce this margin by that percentage. You can see this is reduced here, this current, and this is the characteristic now. So in the power reversal case, this normal operation here means negative side we exchange to each other, so that whenever there is intersection we can have the complete characteristic. Now we'll see it is still not enough, because there is some possibility here. If the inverter voltage is very low, the CA slope is very high, which cause 2 point of intersection and will cause the mal operation. What happens if the voltage, inverter side voltage has gone down, due to your RCI is also changing with your overlap angle, because this commutation resistance is taking care of your overlap period. This RCI, it is nothing but it's responsible for your overlap. If voltage is more down, your RCI is more, slope will be more. Now you can see if the slope is more here in this case, you can see, and this voltage is less this side in any way, you can see we are having the intersection here as well as here. The two intersections here, there, even though you can say we are having so many, 1, 2 and 3. But this current is more, so it will be, you can say this or this will be the intersection, and your controller will hunt which will be the operating point. In this case, we are having one intersection here, here and here of this one. So this may be possibility that you may have a several operating point and your controllers of both sides will start hunting to each other. So what we have to do, we have to see to avoid this characteristic so that we can get proper, you can say, so that there should be only one intersection and we can operate our DC link smoothly. There is two possibilities here because we have to shift only characteristic between this period. So it is possible that we can constant voltage or we can go something else. Now you can see what we can have on this axis here. If this is your characteristic, we can have a constant voltage control here. This is a constant voltage because here is the VD is constant. We can achieve this one. Or we can have another characteristic here, that is here the constant beta control. Means we can, this beta axis here, it is value, it is going, slope is positive. So this slope is the positive of this alpha here, it is a positive characteristic. Or we can have the constant voltage, and in this case whatever you are going to do, always there will be one intersection, and means you are getting only one operating point. So option as here as written, it is to get rid of a constant voltage or beta control is required. Here the constant voltage control worsen the power factor. The constant beta is constant voltage is not desirable because if you are here doing this voltage, your beta may change accordingly to maintain that voltage, and then your power factor will be poor. But here, for assuring that the beta, you are maintaining certain beta, and in that range your power factor will be better. So it is a preferred that we should go for the beta control here rather than voltage control. Now your this characteristic here, now it is changed and we are going to have this characteristic here in this one. So this is the CEA, here the constant beta control, now in this section only. Now if you are reverting here, then this will be, this was your inverter, this was your rectifier, here this is going to work as an inverter, and then again this characteristic will be here in this lower side as well. Means this is repeated. So now you can see this characteristic is used. Still this is not sufficient. I'll come back here, we'll see when your voltage has gone down very tremendous, there is no possibility, means voltage of both sides, means there is a severe fault in the AC system, voltage has gone down tremendous, means you are operating somewhere here, this maintaining current is very, very difficult, and also your valves etc. is highly stressed. So to avoid this, we go for the voltage dependent current order limiters, and this characteristic here is changed. We'll come down to that one, but before this, as I said here, why we are going for the current controller, not the power controller. The reason for this, you can see as here it is written, always voltage or current controllers are used instead of DC power control. It was possible that here we can control the power rather than current here, but we prefer to control the voltage and the current here rather than power due to the following reasons. First reason here, the damping factor in the DC line is small and the controller may become unstable. The damping factor is nothing but your this value, this is resistance of this line. This is very, very small because the damping, when there is a change in the power swing here, the damping, this R value is very less and your power controller may not act properly because due to the I square R, the current which is flowing and R is there very small, so huge oscillation in the power will be there, and there is a possibility your controller may dynamically unstable. Another reason here, the controlling power, the circuit becomes complex and the loses flexibility, because here as mentioned here the P is nothing but your VD into ID. To this control here, the possibility here both can be both will be controlling together or only one will be controlling here, and your controller becomes complex. You see, as I said, here we are maintaining this constant, we are changing one to control the power, but only if you are controlling this, the possibility that this is also changing, or only one is changing, and you know there's all three possibilities are there. Means this can change, both can change, and when both are changing, it becomes very, very complex. And also it is believed that you require a strong communication link between both sides to which one is controlling which one, and even though there is a select here, the changing modes, your again controller will unstable and your line will be run down. So we use your voltage and the current controllers. So another reason for not using the power as a controller, and we are controlling the voltage and currents here in the link. Another here you can see at the low voltage the current required is excessive to maintain the required power. If you are controlling power here, means you are setting some power reference and then you are measuring this value. If the voltage has gone down, what happens? To maintain this power, your ID must be very high, and once the ID is very high, means you are not having any control over this. This is a huge power will be flowing through the valves, huge current will be flowing through this your line, and this line may be damaged. So it is better to use the current. And also at the same time, what happens, you are just firing in such a way that reactive power requirement will be also excessive high. One is the more current here that may damage your converter stations, and at the same time it can damage your line, and also huge reactive power requirement will be there, and therefore it is better to use the voltage and current controllers rather than power controllers at any of the end. Now to have the controller here for the low voltage, that is one of the major concern, especially that happens in the most of the time you are operating your here in this shop. Either this voltage is slightly going up and down, you are anywhere, you are just operating this, but there is a possibility if there is a huge short circuit fault in the both end, what happens, we have to change here, the voltage has gone down. So what we do, we try to change the margin in a such a way, both sides, which we can change this margin here somewhere, so that we can operate at the reduced voltage of this power line. Once you are operating reduced voltage, reduced current, means the power in the link is reduced substantially. If you are maintaining that power, what will happen, if the voltage has gone down, that it is very difficult to maintain the current in the link. You are maintaining this, but these are highly stressed. So what we do, it was found this there is a possibility or this thyristor valves may be punctured or here and there. So we try to reduce here this one, this limits this side, and finally the characteristic can be shifted completely. One option is that we can directly go here, this, and here we are going here. Means what we did, this setting is reduced drastically, both inverter as well as the rectifier end here, and then we can operate on the reduced voltage. But here, this again, this is not advisable. It was found it is not so satisfactory in that case. So it is better that we can directly change this to a no maintain of this reference, because this value has still gone down. So this margin we can maintain. This side we should not act for the current controller, simply it is your beta control. And in the reduced voltage, and this is called the voltage here, it is called voltage dependent current order limit. Means if the voltage has gone down to certain limited less value, the current limiters are reduced, because earlier it was this one, now we have gone down here. And this is called VD call control modification, and you can see now we are having this characteristic for whole operation of the rectifier. So during the AC fault at the inverter end causes commutation failure, it is important to reduce the stress on the inverter valves, which can be achieved by the low voltage dependent current order limit to rectifier control characteristic here, this change substantially. So now you can see this is the characteristic of your DC link controllers, both rectifier as well as your inverter end. Even though always if you are having them sharp voltages, it is sometimes very risky at the D point, B point here. Now people are still changing this characteristic here with some constant here, because whenever there is a sharp here, there is a sudden change. So to avoid this, here another characteristic is used, and this characteristic is, which is this characteristic. We put some circuit, some controller in such a way that we introduce more slope at the corner than alpha, and this characteristic is changed. Basically, this is used in the practical HVDC link controllers. This portion here, we just this sharp point, the change of alpha minimum here, we change in between, we put another characteristic. Because we change from here to here is not sudden, we just go for something, some slope here. So we add some controller so that you can achieve this characteristic and it can go there. So you will find in some of the books, in the modern books, because this is it's a control in some fashion. So now this is the complete characteristic of your HVDC control in here the first quadrant. In case of power reversal, same is repeated downward. And again, always we should have the intersection of the operation. Which one is going this voltage down or this voltage down, we can find all the control. So this is basically the complete control characteristic. Now you can analyze from this characteristic if your inverter voltage has gone very low. Means what will happen? Your inverter voltage has gone down, means you are just achieving here. If it has gone, the characteristic will go down because the VDO I is going to change. Still here you are going to have this ones because this is already beta. If you are going for here another further, here you are operating here somewhere. So these are the parallel characteristic of your here the gamma minimum, and only here this value is changed due to the AC voltage. Now if your rectifier side voltage has gone down and you are operating, now what you are getting? You are getting these parallel characteristics till you are coming here. So wherever you are cutting here, you are getting a characteristic. Means here in this case you are having your operation voltage is this much. So when the voltage of the rectifier has gone very tremendously low, we shift our current controller from this rectifier to inverter side. You can say now this is your inverter, it's controlling current because this intersection is here. If your rectifier end voltage has gone down tremendously low, in this case what happens? Our inverter is taking care of current control, and this is here alpha minimum control here, and this is you can say all the way up to here. But if this side is control coming here, this is still you can say the current is controlled by here. So whole scenario, your increase, decrease, and your rectifier and inverter and voltage can be very clearly seen here. We are operating very you can say stable and the reliable manner with this characteristic. And also it is practically feasible to achieve these characteristics in the rectifier or HVDC link controllers. Now in the total philosophy, it was the characteristic now, and once this characteristic is there, then you have to design a controller for all these characteristics, both rectifier as well as the inverter. Now you can see the control hierarchy. Here we should have a complete the system control as your both inverter and rectifier end. What is your philosophy, what is the power setting, how much you are going to do. This is a whole system control we call, because based on this you decide what will be the power reference, how much power you want to flow in this line in the normal case. So once the power reference is decided, then you have to calculate what should be the current here, the reference. Then we are having the two poles if you are having bipolar. If you are having only one pole, this portion has gone. If you are having two poles, so the both poles should be coordinated in such a way that the same current should flow. It is not that one is flowing the different current. For example, as I said, if you are having a bipolar operation, this is your grounded, you are having another here rectifier. This is your grounded, here the three phase. Now this is one pole, this is another pole. As you know, the current here, it is flowing the same current. If it is a bipolar, In the monopolar, this current may be different, this current may be different, and this total is flowing through the ground. If it is a homopolar, in homopolar you are having the same polarity and the current will be flowing through the ground. In the monopolar you don't have this, so it is only one hierarchy is required. But if you are having bipolar, the same current will be flowing here as well as here. So we have to set the current reference for this and for this the same. So that's why here it is written the pole 2 control, pole 1 control, because this is a pole 1, this is a pole 2. And then we have to go for the valve control. Valve control here, now current reference is decided. Now we have to fire the valves of this bridge as well as this pole together. So this is called your this valve group control, because we are having all 6 groups, and then we have to control based on its characteristic, means your I reference here. So we'll see how this is a control design is going to be there, but whole hierarchy is, first one is this, then we calculate the what is the power references in this link is required, then we set the what will be the current reference value, and therefore we are going for all this pole control here. Here this master control is required, because this master control says that you have to control your rectifier and inverter together. This system control is whole AC/DC network. In the system control, because there is a load dispatch center, you can say there is a substation whole system, and they are deciding how much power will flow in this link. So this is decided by the system controller, maybe the larger aspect having AC/DC network. Then this power reference is decided that this will flow here. Now once this power is decided, the power will be communicated both end. This what power is flowing means rectifier end and your inverter end. Then your reference current is calculated, and this message going to the another one through the communication to the remote terminal, that is your inverter or rectifier. And then we can go for pole, and then the individual thyristors must be controlled to give our desired objective. So this is a control hierarchy of HVDC control here. Now in the here the valve group control VGC, here we are going to control, means we require some alpha, whether this alpha is for your rectifier or this alpha is for your inverter. Only difference, for inverter this alpha is larger, more than 90 degree, and for rectifier it is less than 90 degree, means very small value. Now you can see here this portion will come to later on how they are going to be realized. Different schemes are there to achieve this alpha, but in the clockwise direction I can say we are having the ID reference, then we are measuring the ID from the actual how much it's flowing. We are talking about the rectifier and now this portion. Then this difference is going to your current controller of rectifier end. It is just changing its, it is basically what is the controller. It will give some voltage magnitude, and based on that it will going to some logic, something. So that based on this error here, this is looks voltage, really it is voltage, and this voltage is basically deciding how much alpha it should be changed from the previous instant. Because once alpha was earlier, let's suppose 10 degree, now if there is any change in the current here with the reference value, this alpha should be changed. If the reference here, this and this is equal, this will be 0, and this alpha will be the previous calculated, it will keep on firing. But whenever there is a change mismatch here, it will be there some voltage will be generated, and this voltage basically is given to the some oscillator circuit, and this oscillator circuit generates the 6 pulses, and these 6 pulses again 60 degree delays, it is given to the 6 valves of the 6 pulse converter circuit. So that alpha is here, that is called firing angle control. Now how it is decided alpha, how it is related here, we will discuss later on how this is going to visualize it. Different schemes are there. So this is your rectifier end kit. Here one switch is given here. This switch is acted because this is a negative when there is a power reversal. Because this ID is now going to change, margin we are changing. As I said, if this is going to be an inverter, because power reversal case, the reference here, it is changed in this mode here. And that here current is further is changed here in the margin here, and then we have to change alpha accordingly. So this switch is only closed when we are power reversal is there in the rectifier end. Now this is your inverter side. Inverter side here, we are this gamma, we are this measuring circuit is there. Now you can say how you can measure the gamma circuit. We are visualizing with the sum circuit because we require some zero crossing here always. How you are going to measure? This is the zero crossing is calculated. Now this zero crossing, because you are calculating here, you cannot estimate this zero crossing. We have to go from this zero crossing, because already this is a past. This omega t is changing with the time. We are moving in this direction. So this beta here, your gamma, this angle basically, this is your beta angle. So we are assuming some measuring some zero crossing of this commutation voltage, and based on that we are calculating your gamma. So all this here the calculation part is done with the measurement circuit, etc. And then we are this gamma controller again. If there is some change is required from the gamma, whether you want to your gamma, this is a minimum, this is gamma minimum, you want to here increase the gamma, it is possible, but power factor will be poor, and also we can go only up to the 20 degree of the gamma, not more than that, because if you are going for further, power factor will be worse, because we have the limited reactive power support at that end. So then here we are just error is there and gamma controller is there if there is any difference. And finally this is also generating some voltage signal, and this voltage signal is given to the some pulse oscillator circuit, and this oscillator circuit is giving your gammas. Basically here we are not talking about the gamma here again we are going to calculate the beta, or you can say alpha. In the inverter side here you can say this is a beta, you can say this is alpha as well, because this value is your nothing but from here it is alpha. So basically it is also a alpha, that is a firing angle control, and then this alpha is decided, that is we call beta. I am calling beta because we are using in this equation the beta earlier we used here, but basically it is nothing but the alpha here, that's we are calculating. So this part here is your inverter, this is your rectifier, and both end it is equipped. If you are operating in this mode, your rectifier mode, then this will work, otherwise you have to go for the gamma here in that reversal. And your alpha is the firing angle control is basically decided, and then you are giving the pulses to this. So in the next lecture we will see how these are going to visualize. There are so many schemes, basically it's called individual phase control, equidistance pulse control, so many control schemes people have devised for the better and better controller. Always our intention, again we saw the features that it should require the minimum reactive power support, there should be less commutation failure in the inverter side. All these features can be visualized by the various control schemes, and the next lecture we'll see this all those controllers. So with this I can end this of this lecture 2, and in the lecture 3 we see the various controllers as well for this HVDC.